Schwarz-Christoffel transform discussion. Schwarz-Christoffel transform makes all 2D trivially solvable by transform to separation of variables, solving, then transforming back. Thus, all 2D boundary problems with Laplace easily managed. Example 4.24. Consider the 2D potential problem that occurs when two straight parallel line charges are separated by a distance r with equal and opposite linear charge densities lambda and negative lambda. A. Show that the surface of constant potential V is a circular cylinder and find the coordinates of the axis of the cylinder and its radius in terms of r, lambda, and V. B. Show that the capacitance per unit length C of two right circular cylindrical conductors, with radii A and B, separated by d greater than A plus B, is C. The next equation. C. Verify agreement with 1.7. Determine next non-vanishing order.
D. Repeat with the two cylinders one inside the other. Verify concentric for result when d equals 0. Solution A. Start with getting the potential from a single line charge. See the equation shown. Thus, see the next equation. Using superposition for the potential from the two line charges. See the equation shown. Let's now shift to Cartesian coordinates to identify the circle and transverse dimensions easily. See the next equation. Thus,
see the equation shown. Let phi of surface equals V then have e raised to the V over lambda power equals k equals y squared plus x plus r over 2 squared over y squared plus x minus r over 2 squared goes to y squared plus x r 1 plus k over 1 minus k plus r squared over 4 equals 0, and upon regrouping we get, see the next equation. Thus we have center equals r over 2e raised to the V over lambda power plus 1 over e raised to the V over lambda power minus 1 equals r over 2 the hyperbolic cotangent of V over 2 lambda. And radius equals r e raised to the V over 2 lambda power over the absolute value of 1 minus e raised to the V over lambda power equals r over 2 times the absolute value of the hyperbolic sine of V over 2 lambda.
B. Here we approach the problem by reducing the two-cylinder potential problem to a two parallel line charges problem. We approach it this way because we know from A. that two parallel line charges generate a potential field with cylindrical symmetry. We then use the radius and center relations. At radius A on the A cylinder we have potential V sub A. See the equation shown. Likewise for the B cylinder. See the next equation. If the cylinders have centers above, then the distance between the cylinder centers is see the equation shown. It can be shown that see the next equation. And we get from
see the equation shown that see the next equation is claimed. C. Now consider when d squared is much greater than a squared plus b squared. See the equation shown. Thus, see the next equation. D. Now consider on cylinder inside another. The only change is b goes to negative b, thus,
see the equation shown. And for d equals 0, see the next equation. Example 4.25. Consider an insulated, conducting, spherical shell of radius a in a uniform electric field E sub 0. If the sphere is cut into two hemispheres by a plane perpendicular to the field, find the force required to keep the hemispheres from separating when a. the sphere is uncharged, b. the sphere has charge q. Solution.
A. Let E sub 0 be in the z direction. We've seen that a uniform field near a given axis, here the z-axis, can be obtained with two charges, q and negative q. Place distance plus or minus r along that axis, relative to the current position origin of the uniform field considered. We then take the limit r goes to infinity and q goes to infinity such that E sub 0 equals 2q divided by r squared, shown next. For a conducting spherical boundary, the field is modified by the presence of mirror charges inside the sphere. Using the relation on mirror charges for a sphere we then get for the electric potential. See the equation shown. Showing the charges outside the sphere, see the next equation. Showing the mirror charges inside the sphere.
Thus, for r is much greater than r, and r goes to infinity, only the lowest order term survives. See the equation shown. Using E sub 0 equals 2q divided by r squared, we then have, see the next equation. The surface charge induced on the shell is given by the pillbox formula. See the equation shown. The z component of the force for given angle is F sub z equals 2 pi sigma squared, times cosine theta. The total magnitude of the z component of the force is given by, see the next equation.
See the equation shown. B. Now suppose the total charge on the shell is Q. In this case we can skip to the surface charge formula and modify it by the addition of Q over 4 pi a squared more surface charge. Sigma sub t equals 3 over 4 pi e sub 0 cosine theta plus Q over 4 pi a squared. Thus, the absolute value of f equals the integral from 0 to pi over 2 of 2 pi times 3 over 4 pi e sub 0 cosine theta plus Q over 4 pi a squared times cosine theta of 2 pi r sine theta of d theta equals Q over 16 e sub 0 squared a squared plus Q squared over 8 a squared plus 1/2 QC. The next equation. Example 4.26. Consider a parallel plate capacitor with separation d, where one place has a small hemispherical boss of radius a on its inner surface.
The conductor with the boss is kept at zero potential, while the other is at a potential V such that in the far field region the electric field between the plates appears to be E sub 0. A. Calculate the surface charge density on the plate with the boss, including angular dependence on theta, where theta is the angle from the separator line connecting the center of the boss hemisphere to the nearest point on the other plate. B. Show the total charge on the boss has magnitude 3 over 4 E sub 0 a squared. C. Replace the conducting sheet at potential V with a charge Q directly above the boss on what was the plate's separator line in B. Let the charge be distance d from the center of the hemisphere. What is the charge induced on the boss? Solution.
A. The scenario described allows the boundary with hemispherical boss to be replaced, via method of images, with a new parallel conducting plate with potential negative V, and with a spherical conductor V equals 0, that is the completion of the hemisphere. We, thus, have equivalence to parallel plates plus or minus V at distance plus or minus d on either side of a conducting sphere, at V equals 0. For far field we are told that the plates at plus or minus V are equivalent to an electric field E sub 0 between the plates. We can thus relate the problem to that of a conducting sphere in a uniform electric field, in the z direction, where the electric potential is, see the equation shown. We have the relations 4 pi sigma equals E and sigma equals negative 1 over 4 pi the partial derivative of phi with respect to r to get. See the next equation. For the surface charge density on the boss at angle theta we get, see the equation shown. B. Total charge on the boss is, see the next equation.
C. We now repeat the problem with, but instead of the parallel plate at potential V we have a charge Q placed as indicated directly above the outermost point of the boss. Again, using the method of images, we eliminate the V equals 0 conducting plate with a mirror charge, where the hemispherical conductor is completed to a spherical conductor as before. The two charges with the spherical conductor can then be replaced with the two charges and their mirror charges on a spherical conductor boundary, as described previously. In fact, the expression for the potential is precisely that obtained previously, prior to taking the charges to infinity such that a uniform electric field is seen locally. Thus, for potential we already have, see the equation shown. Showing the original charge and first mirror charge off of plane mirror, see the next equation. Showing two mirror charges, respective to 2 above, off of sphere. Recall that, see the equation shown. Thus, see the next equation.
Positive aq over d times r minus a squared over d cosine theta times negative 1 over r squared plus a to the 4th power over d squared minus 2a squared r over d cosine theta raised to the exponent 3/2 end exponent minus a q over d r plus a squared over d cosine theta times negative 1 over r squared plus a to the 4th power over d squared plus 2 squared r over d cosine theta raised to the exponent 3/2 end exponent times vertical bar 3 lines. Line 1, blank line 2, blank line 3 are equals a and see the next equation, which simplifies to see the equation shown. See the next equation. The total charge induced on the boss is then
q equals the integral from 0 to pi over 2 of the integral from 0 to 2 pi of a sine theta d theta a d phi sigma equals 2 pi a squared. The integral from 0 to pi over 2 of sigma sine theta d theta q equals 2 pi a squared. The integral from 0 to pi over 2 of 1 over 4 pi q times a squared minus d squared over a times d of cosine theta over a squared plus d squared minus 2a d of cosine theta raised to the exponent 3 halves and exponent minus d of cosine theta over a squared plus d squared plus 2a d of cos theta raised to the exponent 3 halves and exponent. Thus, see the next equation.